Unit 9, categorical predictors, but this time instead of dichotomies we have polychotomies, like more than two categories that we used to use. This is from PhD Comics. Do you follow PhD Comics?
Facebook.
Facebooks and PhD Comics. It represents a PhD students' lives, and it's pretty good. I mean, it represents what a PhD student do or professors do. And this is just like from PhD Comics, and no one else of varies. Is your research worth anything? Am I wasting time? And I'm just talking about just like the stuff from type 1, type 2 areas and all those kind of things. And this is one thing. Now we're pretty far away from what we have been trying to do, and we're in Unit 9. And if you look at Unit 10, it's going to be like interaction and quadratic effects. So this time after today, we're gonna, of course, hopefully that we're gonna have just like practice for interactions and quadratic effects. So that's just like we're assuming everything was parallel. Now we just like saying like if it's not parallel, so what's gonna happen?
In Unit 10.
In Unit 10, yes, it's not for today, but it's gonna be for. We again just look at the predictors again. We have nominal predictors and the variables whose values offer no meaningful quantitative information, but simply distinguish between different categories. It's just like in names, it's coming from the name and nominals, like race and ethnicity. So it could be written as 1, 2, 3, 4, 5, but there is no order between any kind of like race and ethnicities, or religions, for example, Catholic, Protestant, Muslims, and Jewish. So you could put anything that over here that there is no order, and for example gender is another one, but it's just like dichotomy, but it's just like nominal variable, and there is no difference between that too. The other categorical variable that we have is ordinal predictors, and this one, that's the only difference when you compare for the nominal ones, the values reflects an order, but not necessarily the distance between the categories. That's one thing. If you're moving for the continuous variables, the continuous variables has two different continuous variables too. They have equal distances between them, but the ordinal variables, even though they prefer, they just like give values to order them from the names, but they don't have any distances between equal to them. Like dropouts, high school dropouts, high school graduates, some college and college graduates. So we can just like order the people based on their graduation, like as like the parent education levels, SES levels. That they always just like categorize them by just like with some kind of an order. And the political views, like liberal, moderate, conservatives, it's not just like one is better than the other one, but it's kind of like in an order again, just like this. So it's kind of in like on a scale from liberal to the conservative to just like in the middle there is a moderate. So you can't just like change moderate to conservative, conservative to moderate. So the moderate needs to be between the liberal and the conservative. It's kind of like that. But it's not saying one is better than the other one. So, but it's that there is an order. So that's just like another type of we can look from the ordinal predictors. It's a different example that you have been thinking.
So we have to identify moderate criteria actually.
Yeah, there's I mean, if you think about the political views, there is a liberal side and there is a conservative side, and there are the people who are in between them. And I mean, for the liberals, I mean, even we can just like categorize them for different levels of liberty and then for conservatism. But it's kind of on a scale. So if it's on a scale, it turns into one of the categories that we have an order. If there is a difference between those variables is equal, then it's going to be continuous variable. But the difference between those variables, so not explicit, it's not the same differences. So we can't just talk about the difference between the liberal to moderate, moderate to conservative, for example. I mean, the differences are from different perspectives. So these are ordinal. The danger we need to be aware of that. We can't include the nominal variables into regression models as predictors.
But as an outcome, we can.
No, outcome is continuous variables in the regression models.
We should
Yes,
try
please.
to continuous.
We can't convert them nominal variables to continuous variables. We can convert continuous to just like the ordinals and the nominals variables for somehow to the other way, but you can't convert a nominal variable or ordinal variable to the continuous variable. You can't go back because the other variables are richer variables, and you lose a lot of things when you move to this part, and you can't go back in here. So I mean, for that reason, if it's a nominal variable, so we don't put that into just like a regression model as a predictor.
Describing sample.
So we can describe sample, we can look at t-test differences, we can look at ANOVAs, mean differences between the groups. These are just groups, but there is no specific order between them. So the numbers doesn't have any meaning, in other words. So 1, 2, 3, 4, 5 does not have any meaning. It doesn't give an order. So I can change the 1 to 2, 2 to 5. It doesn't matter, right? So it doesn't have to be one white. It could be Native American. So the number does not have any meaning inside, and the number. So that's, we can't use those kind of variables in predictors because we're gonna do calculations with those numbers, and we can't do that. For that reason, we can't use nominal variables as predictors. If there is a research that who use nominal variables as just like predictors in a regression model, it's wrong. Trash it. But on the other hand, we can use the ordinal predictors in a regression model, but be sure that's what you want. It's not often. We often include, as we just discussed, mostly continuous variables in the regression models, most of the time. But as we have seen last week, like in the dichotomy, there are cases that we would like to see the effect of the ordinal variables on the regression model, and then we can do. And we've seen examples for dichotomy, just like we have dummy variables 0 and 1, and 0 and 1 had meaning, right? So the no seat belt law to the seat belt law, and 0 means that no seat belt law, and 1 means just like no seat belt. There's a seat belt law in that count, in that state, and whenever we see that number, whenever we put that number into equations, that meant something. So, and we're gonna do something similar in these ordinal variables to do that, but we need to change these variables somehow in order to fit into something that we have done dichotomy. We can't use directly like as is the ordinal variables, and we need to do some kind of dummy variables again in these ordinal variables. And then today we're going to discuss about like what we can do in ordinal variables to put them into regression model if you really need to use them in the
If they have many different predictors, at least one of them cannot be
nominal.
nominal.
Yes, I mean we say don't put the nominal variables in as a predictors. It's not about the number of predictors, it's about the variable itself. It's about, because you're going to do calculations, it doesn't matter 1 or 2, so you need to do calculations, and because that there's no nominal variable that we can do. We can't do math with nominal variables, so that's the main reason behind it. So there's this Windows update coming in here. Yes.
Last week's like presentation discussion, we could like group the how to say regressions. We could look at different groups. Doesn't that work with nominals, nominal predictors?
No.
Can we use them for grouping? No?
We don't want to use with the nominal variables because with the nominal variables you really don't have the mathematical values of
I
it.
understand that.
So for that reason we can put that as a predictor, even if you can like make them groups. Both nominals and ordinals are categorical variables. That means that they convert the variables into groups, but the group's order is not apparent in nominal variables, but the group orders is there in the ordinal variables. That's the reason we can use. Even though we're going to see like we're going to have a data now, and we're going to have both nominals and ordinal variables, and we're going to discuss that we're gonna try to put them into models, and we're gonna see what kind of things happens if we put in the models with those variables into the regression models. This new data set is about wine. There's a Journal of Wine Research. Isn't that fun? That Journal of Wine Research. There's Journal of everything. Whatever you look for, I guess you can find a journal to that people investigate that. And this is just like the Journal of Wine Research. This is 2004 data. Train has done a study on in the defense of the price hedonic model in wine research. Indeed, they're looking for what affects the price of the wine in one of the countries that they're gonna do in here. And
France, I guess
this is just a French wine, but the country is not France. It's which country is it?
No? Bordeaux.
It's Bordeaux.
It's French, right?
Is it French? Maybe I'm wrong. It's a French wine, and it's just I guess it's French. Whenever you see the map, you can, maybe you're better than me in geography, that you can tell us which country is that. They're looking for two variables. One is the area, the neighborhood. The other one is the vintage, just like the year of the wine is being produced. Because the older wines are generally better. But it's not. I'm not an expert. I'm not even knowledgeable about wine.
They are better.
I guess not all the time they're better. If the wine is bad, if it doesn't matter if it's just old or not, it's still bad. Yeah. So some wines are just better because they're good, and they're getting better because of the years, but it's not. So we have the prices for wines. It's in US dollars. There are the wines goes from $13 up to $66, and again because of just non-linearity, I converted that to logarithmic values. So the one that we're going to use the logarithmic prices, but the original prices is on the left. It goes pretty expensive wines over there. The regions, there are 4 regions that just within the data sets: Burgundy, Bordeaux, Rhône, and Languedoc. The Burgundy is being known as just one of the best wines, I guess, if you know about it. Languedoc is just the one that's the cheapest one, I guess. I guess everyone drinks that one. Even the workers drink that one, I guess. This is the map.
It's France. I checked it on the map.
Okay, good. Yeah.
It's north of France.
North of France. Good. Thank you. And this, just like vintage, there are 4 categories: 98 or older, 99, 2000, and 2001. It's just 0, 1, 2, 3. So whenever we know that just 0 is, which is going to be older, whenever we hear the 3, we are going to be, it's just no, it's a newer wine. So that's just number has a meaning, but 1, 2, 3, 4, and the region area doesn't have any meaning.
This 99, 98, are these years?
Years. It's just the production years. It's the producer's 1908 or older years. It's produced in 99, it's produced in 2000, it's produced in 2001. So it's still just waiting. So that's we categorize based on their years or based on their vintage. 2?
1998, at the right side of the 1998.
That means that 1998 and older, minus sign. So, yes, before 1998. And there could be an older kind of just wines, and that would be there. The first research question we are interested in is, do wine prices vary significantly by region and vintage? And that's just you can convert to this question in an education course, a research question. So, do students' scores vary by region and the teacher's experience, for example? So it's going to be like the same type of research question we can still like use in education too. The first question that we've been investigating mostly, and it's kind of like even the t-test that just like it does, even ANOVA does, test does. And the second research question is more interesting. If there is any differences between the prices, region and vintage, two different like analysis, then which regions and vintages are significantly different from each other regions and vintages. So this first test will kind of like tell us there are 4 different groups over there. There is at least one statistically significant difference between the other variables among the groups, and then we need to investigate which one. That's another question that we need to just like investigate. First, it's going to tell us just a general answer, and if there is this is just the distribution of the region, and also when it's compared to the prices. Whenever we look at this data, the 4 variables are in here, the regions are in here, the Burgundy, Bordeaux, Rhône, and Languedoc. It's just like based on the means, I ordered them. This is just like as a mean, this is the highest prices. This is a little bit cheaper, it's a little cheaper, and this is the cheapest prices that we have. And also these are the standard deviations. Whenever we look at this data, the variation within each group, it's differ a lot. The much variable between regions, first of all, the regions, the means are different.
Regions?
These are the regions, the first Burgundy, Bordeaux, Rhône, and Languedoc. And I'm looking at just like between the variables. This is mean, another mean, another mean. The dots are the mean. So they are also different. They vary from each other. And also just like remember the between, the keyword the between from ANOVA. Do you remember the between and within groups? So this is kind of like the 4-2 perspective, between and within. And both variations will help us to check the mean differences is statistically significant or not. And we're going to do regression, but the regression will produce some kind of a result with the ANOVA, similar results with ANOVA.
The logic is the same actually.
Yes, it's the same. Indeed, we're doing the same thing. Same thing. Like in a GLM, general linear models, in SPSS, for example, it produces the same results with ANOVA. ANOVA is analysis of variance. But when we do ANOVA, analysis of variance, we compare means. But why it's not analysis of means then? The test called is analysis of variance. But within this test, we are comparing the means, not variances.
Not like standardized.
What is standardized?
Variances are standardized compared to means.
No. Why then we don't do the same thing for the t-test? The t-test is doing the same thing, right, with ANOVA, but only the number of variables is different. Right?
Maybe the name.
Means on the regression line.
What you mean with the regression line and the means?
For example, we have two groups on depending on one group, and there is a one dependent variable.
Mm-hmm.
We look for when we put 1, the result, and 0, the result. So we last week we do nominal regression. In this case,
Yes.
difference between those lines.
Mm-hmm.
The ANOVA looks for it, but the T looks for directly the means.
T looks for directly the means. Yes, that's right. ANOVA is looking for.
Using regression.
They're doing exactly the same thing. The difference is, there, at least in this case, there are 4 means to compare. Which means that you are going to compare. You need to compare 2 means. If you're going to compare 2 things, you need to compare 2 things. And you can't just look at 2 things. But the variance, you can just look at the variances if there is any differences between the variances. It's looking for the differences in the variance between and within data, and then it's putting into the consideration both within variation and between variation, and to compare the different groups. But the means,
Differences and individual differences.
yes, both of them are just important in this case. But in the mean values, you can do several t-tests. You can compare to Burgundy Bordeaux, Burgundy Rhône, Burgundy Languedoc, Bordeaux to Rhône, and Bordeaux to Languedoc, and Rhône to Languedoc. 6 of them, you can do that. But there are problems with from the analysis perspectives. And for that reason, I'm always using the variances. And it's put the whole variance, like it looks at the data from the whole perspective, from the variance perspective, and then it can compare. It's just like the groups by that. We can do go into details, but the name comes from really that the analysis of variance is investigating the variances, and then based on that deciding whether the groups are different from each other or not. And the variance also has an effect on the mean differences.
I remember you were saying something like this. Maybe I remember it wrong, but like 2 years ago when I got the statistics from you. If like the test looked at the mean differences like between two groups, a lot of two groups all the time, then the errors
Type 1 error increases. So in order to decrease the type 1 errors, so we do different kinds of analysis, and ANOVA is one way of doing that. Just regression or just on these ways, looking for the data is one of them. And we're going to discuss type 1 error very soon again. And I hope that you remember type 1 error, right? Sure. Say. You can buy a cheap bottle from anywhere. Each region's range includes the prices, and here is one of the prices than here. So this is just it's a cheap country. Different prices that we see, and there are differences in the prices, and each range includes just this mean difference.
Did we group the prices too, like low, high, or low?
No, we haven't done that yet. We haven't done that yet in here. Just the prices are in continuous scale. So we're just look at the variations. We haven't grouped them yet. This is an outcome variable, so we don't want to make them as low price and high price kind of thing. So we're just looking the prices as is. But what I mean is just there are different variances in groups, and just between variables, and there are cheap variables in here. Even though just this total overall mean is kind of hits for everyone. For example, if you go to the Burgundy, for example, you can find cheap wines too. You can cheap wines each region. So the even though this is expensive in general, the mean wise, right? This is another expensive too, but the range of this one is higher. The variety is too much. So in these neighborhoods, you can also find cheaper, just wine. So similar prices with the cheapest neighborhoods,
It's a social cultural issue. Everybody brings wine there, so they have to be addressing everybody. Everybody wants to buy Burgundy or I don't know.
Everybody wants to just have the wine. There are workers too, so that they're just people who seeks for cheap wines. But still, even though just in higher prices, still you can find just the lower prices.
So the overall means 2.75?
I don't think so. If I said that, I think it's wrong. But it's just looking at just a value that just covers everyone. It's about cheap prices. So
The green line.
the green lines.
Overall mean?
No, it's not overall mean. It's just any value that's just lower prices. 2.75. It just show the variance. So between I'm sorry, within variances is too much, and different categories. So if the within variation is not that much, I wouldn't find cheap wines in, for example, in the Burgundy. So because the mean was higher, and if it's small like this, it was gonna end up right in here. and it wasn't going to be fined. Now you can't find just like the same prices wines within all regions. But now, because of this huge variances on these neighborhoods at least, makes you to find the similar result. I mean, you don't say wine, but you say just quality of schools. You can find good quality of schools, or just low quality of schools. So in every region that you can find, because of the variance that we have. The question is, another question, is there a heteroscedasticity among this variable? Is it heteroscedastic distribution? It seems so. On the lower end, more variation. In the higher end, it's just low variation. So it looks like it's not homoscedastic. It's a heteroscedastic distribution here. So the mean's just right in here. But whenever we look at the variation has changed dramatically from this part to that part. So this is from vintage perspective, the same data. Again, we're looking for the prices, but this time we are looking for the vintage years. 0 was the 98 and older, 2000, 99, 2000, and 2001. And the same thing that we can look from here, the between the variability again between variables. The means are in here. The means are somehow different. And the older wines are more expensive than the younger wines. That's one. We see the same kind of patterning in here. Again, you can buy cheap wines from any vintage. Older prices also has cheaper wines that you can find. The within ranges is great. That's what we see. But the difference between the other one and this one is this is less heteroscedastic. So the variation difference between within variation, whenever you compare the within variation, so they are somehow similar to each other. So it's just less differentiation between the within variation and just about the 40s that we have. How much credence should we give to trust? Should we give to observed difference between the group means? From a numerical perspective, the vintages has mean differences, right? 3.46, so you can convert to the real money to those this is just because logarithmic values, e to the power of 3.46 kind of things. 3.20, 2.30, 2.85. How much credence, how much trust should we give to observed difference between the group means? That's a question that we need to ask. Why are we asking that question? Even though we see that there is differences,
We don't know whether it's
we don't know if it's significant. Yes, that's true. What else? Odd. They're asking for your help. The question is on the top. How much credence, how much trust should we give to observe differences between the group mean? We know that there are differences between the group means, but I mean, is there really group differences between the vintages? Trust.
Can it be caused by another thing? Or are you asking for this?
Are they really different? They seem different, but
They seem different, yes, but are they really different? So there are a lot of variance in here. So whenever we consider about the variances, the situation can be different. So so look at the variation. There are huge variations in here. The variation within variation has an effect on our results. So that's what an analysis of variance is just considering. Between variations, these are the between variations. there are between variations, but also there's like within variations, and this within variations will have an effect on the results. That's just like what we are asking for. In what context can we place these observed differences to evaluate their magnitudes? So, this context that we're dealing in here, like in the research context, again, it's gonna like not talk about the variation in here. There are a lot of variation in here. So how much this context, the variation we have, will affect our trust to our results in here. That's another thing that we're gonna look. So now we're gonna look for that. So the variations, similar variations, and the variations are kind of big in here. That's just like important. Let's investigate this context issue, and let's look at for this trust issue for the mean. So we have 3 different variables in here. This 3 different variables has the same means. Like the between group variations are exactly the same. 3 different data sets, 4-level categorical, just like a predictor, where the 4 means are identical each. Within group variation provides a key context for evaluating the magnitude of between group variations. So that's
Those are between group.
this is between group, but we are going to look at within group. So within group variation provides us a context. That's like how much attention would you give to these observed groups to group differences means if they were equal and moderate variable within groups.
The individuals of the groups are very varying from each other.
Yeah, they're varying from each other. That's just like moderate variable within groups. They overlap a lot. If there were equally but little variables within groups. So now you look, for example, find a price in here, okay? Draw a line. You can find the same quality of whatever you're looking for within these 2 groups, but you can't find within these 2 groups. And if you try on the other way, you try from here, you find the same things from here, but not from here. Bless you. But this is much different, even though the same means. So this is within even if you consider the variation, this is different than the other ones, with the whole variation as well. But the variations increase. Look at that. It's almost covering everything. That just like that you have. This is the context that's going to change the results. Even the same means.
For more variation within group creates less variation between groups.
Not variation, but the analysis of variance was not going to produce, for example, in this case, even though similar, the same means, this is not going to give you statistically significant difference. Probably this is going to give you a statistically significant difference, but not between all of the groups. It's most likely that this is going to give you a statistically significant between all of the groups, even those with the same means. The variation will have an effect on the results. So that's the reason whenever we do the analysis of variance, we look for between group variation and also within group variation. So the 2 thing is important.
So here there are 3 different contexts. Data.
3 different data, 3 different contexts, yes.
However, all have the same meaning.
Yes.
All categories.
We assume that they have all the same, just like variables, they have the same means,
Okay,
but different variations.
What will be different?
The results will be the
Not different. Can we make an interpretation by just looking here?
by just looking at what kind of interpretation that you
Can
ask
we
for.
make, I don't know.
So we're comparing these 3,
The
or
results will be different, okay?
yes,
This is the most important.
that's the most important thing. Even though you have the same means, you look at the in groups that are different, but you're going to find that these are not going to be different. This is somehow different, I guess. We need to see that. It looks like this. But this is going to be different. This is going to be different from this, from that, from that. Maybe these 2 not. But these two, these like pairs, that, and this that is going to be different. But this is not going to be different than this one. It's most likely. This is not going to be different than this one. Maybe this is different from this one. But this is not going to be different from even this one. They overlap too much. That means that they share a lot within because whenever the variation increase, it's going to be just like you can't find the differences. It's going to be difficult.
Can I ask something?
Of course.
How do we calculate between group variation? What
Within?
do we do? Between group variation. How do we calculate it? Like what do we do there?
So
Mathematically.
we are calculating just like the means, and then just like we're using those means to compare the mean group means, and that's just like comparing that variation to overall variation.
But looking at them, like all of them at the same time, right? Not separately, but
Not separately, yes, all of them at the same time. Within group, you're looking individual separately, but within groups, you're looking all of them at the same time, the data. And analysis of variance is giving, the analysis is giving both just like the values to us, between and within groups. So remember that between and within from the analysis of variance tables, right? That is as this one. So that's the reason we need both of them to analyze them, to just like calculate them, and for the results. That's why we do that.
Şu istatistik derslerinden sonra aklımda kalan bir his yanlış
So we stopped in here. Two variables. One is for nominal. The other one was ordinal variable, and then we discuss why we can't do this one. Okay. How do we include a polychotomy in a regression model? Creating a series of 0, 1 dummy variables. Now we're gonna use these. Even though we're gonna use this one in a regression model, we're gonna see the results. I mean, the results will not going to help for us, but we're gonna end up how we discuss this regression results in here. So we have regions in here, 4 different regions, and 4 different regions. If we put that in 1, 2, 3, 4, we can analyze them in a regression model, and how we can convert this one into a dummy variable that we can put into some kind of regression model, and then it's going to be like meaningful in here. So first of all, the variables are in here, like the regions 1, 2, 3, and 4. The first thing, we need to create a series of 0 to 1 dummy variables, one for every value of the categorical predictor. So what I'm gonna do is, like, I have a variable for burgundy, which is going to be as 1 and all other zeros. So this is like this polychotomy, it converts into a dichotomy. Any variable now.
Burgundy, it's 1. If not, it's 0.
Yes, if it's burgundy, it's 1, and I can compare to burgundy to every other regions. So now I can use a regression model. So it's just like I converted the variable into something that I can use in a regression model. I can't use this one as an area model because it's just like I have 4 different variables, 4 different segments. But now this is a new variable called burgundy. If it's 0, not burgundy. If it's 1, it's burgundy. I can do the same thing for Bordeaux. If it's Bordeaux, it's 1. Otherwise, it's zeros. Same thing for Rhone. If it's Rhone, for 1. If it's not, for zeros. I can do the same thing for Languedoc. It's just like 1 and 0. So instead of 1 variable, I have 4 different variables now, and 4 different dichotomies, 4 dummy variables. Collective law 4 dummies identify every one specific region. So still, I just can talk about different regions, but not in 1 variable, but in 4 variables. But on the other hand, 3 dummy variables would also be sufficient to identify every one specific region. So if we focus on these 3, for example, and if we only analyze this part, these 3 variables, if this is 1, the rest is 0. So I know that this is burgundy. If this is 1, this is burgundy. If this is 1, this is Ron. If all of them are zeros, it's going to be Languedoc. I don't need the fourth variable indeed. With 3 variables, I can cover the whole 4 variable, like 4 levels of one variable into 3 variables. So instead of just 4 different dummy variables, I can just eliminate 1, and then I can just use 3. And one reason for eliminating one of the variables like Languedoc in here, if I have that one, and if I produce a regression model, what kind of problem that I would have? If I include 4 of them in a regression model. Yes, instead of 3. This 4. Why I'm trying to remove 1. First of all, I can just define with 3, all of them. Think about the regression models that we discussed. Think about the problems we had, and then we just did things. For example, composite variables, removing a variable to prevent that problem.
Is this about complexity?
No,
The reference?
no. Collinearity. If I have this variable in here, that's totally collinear with these ones, because this is not adding anything new to this data. So this 3 variables already telling, even if I add this 4th variable. So they go at the same direction, that they're collinear. So for that reason, I don't need it. If I have it, this is not going to add anything to the data. Yes?
Isn't collinearity also isn't it created by the 3rd variable to a degree?
This one? No, why? For how?
Is it only the 4th variable?
No, it's not the 4th, one of the variables. Any of those, it doesn't matter. So this is going to be our reference variable, but it doesn't have to be this.
Okay.
So I need to choose which variable is going to be my reference variable that I could just take as a base. It's just why I choose the Languedoc? Because it's the cheapest one. I mean, I don't want to choose something in between. Then I could set this one as a base, as a reference level, and then I can talk about after that. I would maybe think about the burgundy and then go to the other direction, but generally as an intuition we choose the lower end, and then we move on that one. So because I know that has this smallest mean, the lowest mean that has, but we only to remove one of them, not just specific one, any of those.
So Languedoc is reference?
Yes, we're going to use that one as a reference because I'm not going to use it as a variable. It's not going to show up as a predictor in the variable and in the regression model. But whenever I converted this one into a regression model, the intercept would be the Languedoc. Because if everything is 0, what's just in our regression model, remember that if everything is 0, what is left? Languedoc is left. Yes, that's going to be, another name is intercept. So everything is 0, that just tells Languedoc. If everything is 0, it's just intercept. That means that intercept is the Languedoc. So that's the reason I don't need that one as a variable. That's another just explanation why
I just if the order was different, it didn't have to be Languedoc.
Yeah, it doesn't have to be. I mean, so the decision of choosing which one as the researcher's choice, and the researchers need to choose with a reason, with a rationale. And for this case, the rationale is Languedoc is has the lowest mean, so I'm gonna take it as a reference point. For that reason, I just sacrificing the Languedocs from my data, and I have all the other just 3 variables that I have. These 3 dummy variables are mutually exclusive and exhaustive. Mutually exclusive means
They include each other.
They don't include each other. Mutually exclusive. So if it's like the one, the wine is from the Burgundy, it can't be from Bordeaux, it can't be from Rhone, it can't be from Languedoc. The exhaustives means these three dummy variables covers every variable in this, every data points in this one. So it's just like covers all of them. Exclusive and mutually exclusive and exhaustive. For that reason, so the fourth one produces a 100% collinearity with this one. Because with these three, I can cover every data set.
Even the Languedoc's data. I
Yes.
can cover.
All of them are zero. That's just like that means the Languedoc. Yes, I.
It's basically long Languedoc then can have the zero as a group.
As a predictor.
I mean, when we do one for each group,
Yes.
indeed, the rest, the Languedoc,
Uh-huh.
then will have a zero,
Zero.
as a group number.
And then it doesn't have any variation in it, so it's not going to be a variable. It's just like constant.
I mean, as a nominal variable.
If
we
it's
call
all
it
zero,
as a zero.
huh?
We call it as a zero.
Yeah. If you call it a zero, it's not a variable. It's a constant. I mean, if all is zero, is the variable? Zero, zero, zero,
Group
zero.
number is zero.
What do you mean group number is zero?
We determine one for each group in every column,
Yes.
for each column. Then we don't need to give one more one because it is the rest group and
Yes.
just as the zero is a number. The group.
If you say so, yes, that's it. I mean, so these zeros represents that just Languedoc.
Yes.
So if you put a Languedoc and you put zeros,
It will be second.
it's going to be the same thing. So that's the reason we can remove in here. And so this is another important thing: being mutually exclusive and exhaustive. So these three covers everything in here, and they're not overlapping each other. Step 2 is include all but one of the dummy variables in the multiple regression model. For K group, we need to have K minus 1 dummy variables. So this is a general case. If you have K variables, so for dummy variables, you can have K minus 1 of them. The regression equation. Just let's go for our ones. So y equal to beta 0 intercept plus beta 1 Burgundy plus beta 2 Bordeaux plus beta 3 Rhone plus epsilon. Think about it like this variable is 0, that variable is 0, that variable is 0. What we have is beta 0. That beta 0 represents the Languedoc. So that's the reason I just can easily remove that from my analysis. So this is going to be our reference category. Here is our data and its distribution. So the wine distribution, and there is the regression equation on top. And let's analyze what these means in here. This is the mean for Languedoc. That means that if every other variable is 0, it's going to produce the intercept, which is going to be the 0, beta 1. I'm sorry. The mean for Languedoc. If I put zeros in here, 0, 0, 0, that produces a beta 0, y hat. It's going to be the mean for Languedoc. And this is the reference point that we have.
This line there represents the vintage, right?
This line represents the prices, not the vintage. So we are using two different regression models, one for region
One for vintage.
prices, and the other one is like vintage for the prices. Two different analysis. We have one research question, but two different sub question. One is for the region, the other one was for the vintage.
I thought we would do multiple regression. Like.
That's something different. So if you put two different outcomes, that's going to be two different things. So now we're doing two different analysis.
Okay.
The price is one outcome that we're gonna use here, and we are using these. Just we are not controlling for now for the other variables. We're doing the simple progression in here, just to analyze like how these nominal variables can be converted into something else, dummy variables. So this is going to be beta 0, and this is going to be our intercept. So this intercept has a meaning now. Normally, if you remember from the simple linear regressions, intercept didn't have any meaning. It started to have a meaning from last week, which is going to be the dichotomous variables, like as the reference variable. It's the same thing happening here. The beta 0 has a meaning in here. So if we take look for the burgundy, and if we give 0 other than the burgundy, what we'll have is beta 0 plus beta 1. So it's going to be from here. The beta 1 is not going to give the mean of the burgundy. Beta 0 gave the mean of Languedoc, but beta 1 didn't give the mean for burgundy. Beta 1 plus beta 0 gave the burgundy. So beta 1 is used as the difference between the mean for Languedoc and for the burgundy, because we take this as the base. Whenever we remove that variable, we set that as just like the 0 level for this. That's the reason the beta 1 is the distance from the beta 0 to the mean of the burgundy. Same thing happens for the Bordeaux, and we can do that the same thing. It's here it says the beta 1 estimates the price difference between the average burgundy and the average Languedoc. So here the same thing happens for the Bordeaux. Again, like the beta 2 represents the difference between from the Languedoc to the means for the average mean for the Bordeaux. Same thing happens for the Rhone. This is for visual representation of this linear regression model that we have.
So may I ask the research question?
Shay.
Are we focusing on the first research question?
Yes. In first research question, we have 2 sub questions. We are focusing for one, the region. Do we have any price differences based on the regions? So if there is a statistically significant difference based on the different regions on the wine prices, that's the first sub question that we are investigating now. So the other question was going to be the vintage effect of the vintage on the prices. So this is an analysis table for them, for regression equation table, but we use these variables now instead of a region, the region's name as a variable put into regression equation. So the nominal variable converts into dummy variable, and then we use that dummy variable into just like analysis. So we said nominal variables can't be used in the regression model, but nominal variables can't be used as is in the regression model. But if we convert them into dichotomy, we still can use in the regression model. So that's what we are doing now. So the model is statistically significant. Wine prices significantly vary by region. We rejected null hypothesis. The null hypothesis was each of the wine prices were equal from the Burgundy, Bordeaux, and Rhone. And the hypothesis, we are not talking about just like Languedoc. The Languedoc is just like for the intercept, but it's going to be something different because it's the base reference level. So we are looking for all of them are different or not. Beta 0 is different or not. RMSE, root mean squares error, estimates the average within group standard deviations. So each one has just like their own standard deviation, remember that? So this root mean square error averages those standard deviations. it says a mean 0.35, just like the root mean squares error within the data set that we have as an average. About 1%, 1/3 of the variation in price is explained by the variant, by the region that we have. That's just like, let's put them on that. The intercept provides the estimated mean for the reference category, which is going to be the Languedoc, and just like the estimated mean log price for Languedoc wines is 2.65 in logarithmic values. We can convert into the dollars, which is about less than about like $15 e to the power of 2.65. That's just like the intercept has a meaning in here. Normally in regression model, intercept general doesn't have a meaning, but this intercept has a meaning for us. But this t-test for the intercept doesn't have a meaning. It's just looking for whether the zero, Languedoc is different from zero. Languedoc is already zero, so it's looking for the difference has no meaning. Each regression coefficient estimates the differential between the mean of that group to the mean of the reference group, not the overall mean. So that's the important part. So each regression equation, these estimates, now where's my mouse? It's here. These regression equations is comparing to the mean of each group to the reference group, to the Languedoc, if they are different from the Languedoc or not. So that's just like t-test or compare. Yes, but I mean that's just can be forgotten. So that's the reason just like we're focusing on here, because generally in regression models we are looking for the general mean, so overall mean. But in this dummy variable, because we set a reference, so that's our just like thing that we are comparing. Now these t-tests means that Burgundy is statistically different than Languedoc. Bordeaux is statistically significant different from Languedoc, and it's the same thing. Rhône is statistically significant from Languedoc. So that's why we are looking from these perspectives. But we don't know yet if there's significant price difference between Burgundy, Rhône, and Bordeaux, etc. We looked for the reference values, but we haven't looked for each of those yet. We could analyze the difference between the reference points, but we couldn't look for if there is any difference between the other one, Burgundy, Bordeaux, and Rhône. So that's
still it is early to answer the first research.
No, it's not early yet. We already said that there is statistically significant difference, at least one of them. So that means that region has an effect, but we don't know which region has how much effect on that one. So that's the second research question we're going to investigate. Which one? It's kind of we're coming to postdocs, primary analysis, and those kind of analysis where we are coming to that. But we answered the first part of the question. Yes, there is effect on the region, on the prices. So this is the regression equation to predict the prices. 2.65, the reference point prices, and then we could add 0.74 for Burgundies, 0.60 for Bordeaux, and then 0.42 for the Rhône. So that's just gives us a price for the categories in here.
So is it significant to choose reference category?
What you mean is it significant?
If we chose Burgundy, so
Again,
the same,
we would find the difference, but when we set the Burgundy as a reference point, it was going to take Burgundy to Bordeaux, Burgundy to Rhône, Burgundy to Languedoc. So I'm not sure if it's going to find Burgundy to Bordeaux and Rhône, but I'm sure that it's going to find Burgundy to the Languedoc at least, because I find the reverse, Languedoc to the Burgundy. So if I set the reference as a Burgundy, I know that at least I'm going to find the difference between the Burgundy to the Languedoc. So then I'm gonna say like at least there is one. So one is enough to say that this has an effect on that one. So it doesn't have to be more than one. Remember ANOVA. So ANOVA tells us at least there's one significant difference. So that's just like what it's checking. It doesn't matter where you start. It's gonna tell you like there is one in here. For that reason, I mean, choosing either top or bottom is important to have these analysis. So this is again for we're fitting the data to the fitting model data to sample data. Here is the estimated mean for the reference category. The estimated mean for the language is 2.65, which is on the data point right here. This is the mean difference between the Burgundy and Languedoc means, 3.39 to the 2.65, 0.74 comes in here. Parameter estimates for each dummy variable is estimated difference, and means between this category and the reference category. So this is going to be this part. So that's what we see now. So then we can calculate the mean for the Burgundy, for example, 3.39 by just looking at this reference point and by just looking at this beta value. Same thing happens for beta 2, and also same thing happens for the ROM.
For model tell us where is the difference between.
Where the difference is, yes. That if you run 4 different models, it tells us. But generally, we don't run 4 different models to test. We choose one model and then we do other analysis. But it does tell. It does tell, yes. If we run 4 different models, it also tells us where the differences are. That's right. Understanding the consequences of changing the reference category on estimated regression coefficient and hypothesis tests. The intercept is always the estimated mean of y in the reference category. That's just like for Languedoc, Rhône, and Bordeaux and Burgundy. The parameter estimates and associated tests for each dummy variable will change because they always refer to the estimated difference between the mean and for that group. That's what we have said. Even though there's a significant variation between the regions, not all regions are significantly different from each other. That's what we know. At least the example for Burgundy to Bordeaux in here. The estimate and associated test for all specific contrasts remain the same, although the sign will change and reflect the reversal and contrast decisions. That's what we also discussed. These are changing. So this is going to be just like different points in here. Do wine prices vary by region? If so, which regions are significantly different from each other? This question is res. So we're answering by this to yes, degrees of freedom, and this p-values, f-test. Are we sure that we know which one? Not yet. So that's like what we are trying to. We focus on minimizing the type 1 error when we set p equal to 0.05. We would like to limit the rejection error that we have. But as we conduct multiple tests, the type 1 error for the family of tests grows. Each one of them has 0.05 of type 1 error, 0.05 type 1 error. And just to consider about this one, there are 6 times 0.05 type 1 error. Totally I have 0.3 type 1 error now within the family of tests doing the same thing. So if I look from the overall perspective, my type 1 error is increased too much. I need to do something for this. What can I do? What can I do for... Yes, what can I do? What can I do? What can I do sometimes? Everything happens. Everything happens.
That's the statistics.
Big games are even the other games.
Is like
Effects of making multiple comparison on the type 1 error for the entire family of the tests. If there's one test, we use just like, of course, one. If two, the total family type 1 error increased to 0.10, 0.25, 0.50, it just like increased too much. So then we need to do something, and instead of just like taking individual tests for 0.05, let's say the 0.5 for the whole family of the tests. And that type of correction is called, remember the name of that correction?
We don't remember anything.
We haven't discussed that one. Maybe you remember. Using the 0.05 instead of individual tests and using that 0.05 level for the entire family of the tests. And that correction is called, remember the name when I say that, Bonferroni. Remember that Bonferroni correction? So it's Bonferroni correction that we try to just like use the whole value in here, and then we divide 0.05 into 6 in this case. And whenever we divide the 0.05 into 6, what do we get? If you divide it into 2, it's 0.025. If you divide it into 3 again, 6. We're gonna see that. So, there are multiple comparison procedures. Bless you. There are many tests to do these kind of multiple comparison using, like Duncan's multiple range test, Tukey's honest significant differences, Sheffey's multiple comparison test. Remember the names from somewhere, the Tukey's, Sheffey's. Huh? Where do you remember that? It's ANOVA postdoc. So on the background that they are doing those kind of like corrections, and just like the other one says Newman kills multiple comparison sets, Benjamini, and as you see that they're names and the people are producing those kind of just like correction factors, and the Bonferroni methods that we use a lot, and in issues involved in selecting an approach, is it going to be a prior or post hoc comparison? Is it going to be a simple or complex comparison? When we say simple or complex comparison, are we comparing everything that we have? Every other just like variable we would like to compare each of them? Or are we just going to have like some complex comparison? I'm going to add these two things together and I'm going to compare it to the other thing. I'm going to compare that two things to compare it to the other thing. So I'm not going to compare everything, but I'm going to have like some complex comparisons that what I'm going to do is going to decide which method that I'm going to use. Is there a clearly identified control group? If there is a control group, that means that I'm going to compare everything to the control group. That's like, I have, let's say that Languedoc is our control group, and then I'm going to compare to the Languedoc, everything to the Languedoc. That's most important that for me. So that's going to decide which comparison that I'm going to do. The number of just like, the data sets are equal or not within the groups. So that's also like if you choose Tukey's and Sheffey's and then the other things in the postdocs event, they ask you like how the numbers are equal or not. If they're equal, you use this variable, and if it's not equal to the other, just like things. And these are the things that we makes us decide which kind of thing that we use. But the Bonferroni correction is used a lot, and in this case, this for 2 tests is 0.25. That goes us like for 5 tests 0.1 level. We divide the original p-value to the number of tests that we have to find the individual p-values for each test. So we are splitting the 0.05 into the number of tests that we have. There's a link in here that you can go. This is like the SurfStat t-distribution calculator. It's just like calculates the probability distribution for you whenever you give the numbers. Just like this, it's a very simple website. If you would like to, you can go there. Here, 6 variables that we have. 6 comparisons, I'm sorry, not variables, 6 comparisons. And the p-value for that one is calculated 0.0083. So now, instead of just like looking for 0.05, I'm looking at 0.0083. Or I'm looking at these critical values like 2.75, 2.69, 2.64 based on the degrees of freedoms. If the degrees of freedoms increases, the critical value increase. If the degrees of freedom, if the number of tests increases, the value increases. If the df increases, t value decreases. So if you look at from the end points of the data set, the lowest one is 1.96, about 2. The highest one is 3.72. So it's not going to be beyond 4. If it's beyond 4, there is no need to even think about it. It's just going to be just like t value is bigger than that, so it's going to be statistically significant difference. So most of the time the p-value are 0.000, even it doesn't say anything to you. So it doesn't matter if you do the von Ferroni correction or not, it's going to be statistically significant difference. So that's what we do. So now we're going to look at the values from this perspective now. What changed? The mean Rhone price is now indistinguishable from that of Burgundy and Bordeaux. 0.02 used to be statistically significant difference. This used to be statistically significant difference. Now it's not. They're not statistically significant different. If I consider from this von Ferroni correction perspective, which we need to make some kind of correction in here. So the way we interpret is going to change by that. There are still these differences if you compare to the Languedoc to Burgundy, Bordeaux, and Rhone. They're still statistically significant different from Languedoc.
Are these values after the correction?
No, these are the correction is we do 0.05. This is the same table. The table hasn't changed.
Okay.
The only thing that we compare, either t-value or 0.05 is changing. We used to compare this one to 0.05. Now instead of just a 0.05, we are using the individual test for 0.0083.
Okay.
And then we conclude, our conclusion changes. This is not going to be statistically significant different, but these are still statistically significant different. The mean Bordeaux price is still indistinguishable. This wasn't used to be statistically significant. Still, it's not statistically significant difference. So we can't still reject the Burgundy and Bordeaux. These are similar price range, and this is much cheaper than the other one. That's what we know. Research question 2. If so, which regions are statistically significant difference? Only Languedoc is statistically significant different from all three others. So that's just what we find in here in this analysis. So uncontrolled ones are in here. I'm sorry, I was wrong. Nothing has changed. Sorry. So this is a different study, an interesting study about astrology. From wine to astrology. They studied 223 diagnoses, like neck fractures, heart failure, kind of diseases, or diagnostic things that they do in a hospital, that accounted for over 90% of the whole hospitalization in that region. And this is Journal of Clinical Epidemiology, by the way.
And they included data from astrology.
Yes, they did.
To mock it, I guess.
The question predictor is astrological sign, which has the two categories, and they just like have from the whole Ontario region, all the residents from the Ontario region, about 10 million people. They use all of them, all of those data, and use half of them for hypothesis generating sample, and the other half is to hypothesis validation sample. So they're trying to find if there is any relation between the astrological signs and the diagnosis that they have. Do you think that will they find? Will they find? Maybe.
You can't
Maybe it's a very political answer.
You can't like use something like that doesn't exist as a variable.
What was it again?
Astrology is like bullshit. It's not scientific.
You're re-recorded.
Okay, I can say it louder. It's not scientific, it's just birthday.
But they sometimes give the dates of earthquakes and they
Yeah, they do. Believe me, they do.
Let's see what happens in here. Of these 223 diagnoses, there were 72 for which residents from the one astrological sign had a significantly higher probability of hospitalization, p ranging from 0.0003 to 0.0488. This focused on 24 diagnoses. Lowest p-value was 0.0006 for Taurus. I don't know the Taurus and the names for that. Not sure.
Wow.
You can check. For Taurus being 27% more likely to have diverticula of intestine. So if there's any Taurus, they found for the hypothesis generation, and they tried to validate this one. Studied the 24 diagnoses and the second sample. Only 2 associations remained statistically significant. Leos were 15% more likely to be hospitalized for gastrointestinal hemorrhage. I don't know how to spell that. Sagittarians were 38% more likely to have fractures of the humerus. How many multiple comparisons that we have? It's the number of categories minus 1 divided by 2 is going to give the number of categories that we have, like the total comparison that we're going to have. We have 12 categories in here. If you multiply 12 with 11 divided by 2, it's 66 comparisons that they're going to do like in here. And whenever you do 66 contrasts per diagnosis, and then your p-value turns into be p.000003485. T-value is decreases at 4.64. So then what happens if I have that kind of a small p-value? What would happen?
Nothing.
It will be very hard to find differences.
It will be very hard to find the differences. Even if there is a difference, I probably won't find that difference, right? And we call that type 2. Type 2 error. Our aim was to decrease the type 1 error. But whenever we are decreasing the type 1 error, on the other hand, we're increasing the type 2 error. Just like we're losing one, we're gaining one, we're losing another one. So that always happens. So and to show this one, there are other studies too. If you use the Bonferroni correction in such kind of like comparison with a lot of contrast over there, then you're gonna more likely do a lot of just like type 2 errors.
Can you repeat your last 1 minute?
So as the type 1 error decreases, that's why we try to do that, decrease the type 1 errors, then we increase the type 2 errors. Means that we have such kind of a small p-values that we are not going to find out even if there is a real difference. Because of that, we have very few low probability values that we are seeking for. We're not gonna find out. It's not because there is no difference, because we limit it too much. So having too many contrasts and using the Bonferroni correction increase the type 2 error too much. So that's dangerous. If they adjusted it for multiple comparisons, none of these 72 tests would have rejected. If they had adjusted for multiple comparisons, none of these tests would have rejected either. So the result will change. So that's just like not important. So we need to be careful about like again the choosing the correction. Bonferroni correction that we use a lot, but if the number of comparisons is too much, it just like diverge from the real results. Just set that we can just like see the data set in here. This is the old data set that we have. Choose the 2001 as a reference, year of 2001 as the reference category. Again, we have a significant model. That means that wine prices vary significantly by vintage. We can reject the null hypothesis. Root mean squared estimates the average within group standard deviation, which is going to be about like 0.38. The variance explains about 23%, about like 1/4 of the variance is explained by this model. The intercept provides estimated mean for the reference category, which is going to be 2001 prices, and it's 2.85. The regression coefficient for each dummy variable estimates the mean differential between the group and the reference category, the same thing. It's in the log prices, and it's significantly higher than that of wines from 2001. So the younger wines are cheaper, that's what we know, and we found that just like the older wines are more expensive, statistically more expensive than the other one. This is going to be our regression equation that's produced by the categorical variable. Because this is a categorical variable, the order that we have, the years, and we have a meaning, and the order also represented in this beta weights.
It's a yield. Why we use it as a categorical? We can use it as
Continuous variable too. We can do that too. I guess we're gonna do that too, but sometimes it's meaningful to use years as a category. So these say all of the wines produced in that year. All of the wines produced in that year too. So generally people are discussing whenever talking about the wines. It's not just like talking about this year is this month, kind of like continuously. So that year's wines. So I mean the year is important. So
some of the years have maybe better products.
yeah, I mean the grapes that for that year is affecting that year's the quality of the wines, for example. It's like the regions as well. So for that reason, people might prefer as a categorical variable.
And also they do not produce wines like ongoing through the year. There's like some specific months
Yeah,
that they actually get it from the grapes, extract it, and produce the wines.
and then they just like walk on the grapes. I haven't done it. Yes. It would be fun, I guess. I'm not sure, but nimet ama basılmaz onlar da. This is the equation that we have. 98, 99, 2000, and 2001. As the year increases, the price decreases. We control for the year, it continues as a year. So with the area, it didn't change anything. Still, just like the Languedoc is still the cheapest one and statistically significant than the other one.
Understand.
this
Clear.
yes, that's like we can produce those from our regression equations. The computer doesn't like the SPSS or the software. It's not producing for us,
Yeah.
but we can produce them easily. I mean, that's not very difficult. Just like
Hocam şu hızlı ilerliyor bu sefer. 28 santim.
evet,
Biraz daha okuduklarımızı anlamak biraz daha anlamlı hale geliyor.
used by the means. This is if you put into regression results, the region is a continuous predictor that produces significant results, the F value. Here is that. It says there is just like a beta weight in here for that one too, region 2. That means that for every unit there is a 0.28 difference in the prices from the logarithmic perspective. It decreases from that. Remember that was going down from here. But the idea, even that it also explains for 34% of the variance in here. But because we can't use the nominal variables in the regression models, even though you find that result, it's going to be incorrect. So this is just like statistic significant difference. Being this moderately high doesn't mean that this model is a correct model. So
You're violating the first step.
Yeah.
To look at the
The
type of the variable first.
So we can't use this model because the variable is a nominal variable. So that's the reason we can't use this variable, the model. So I mean,
But if you put this in SPSS, it will extract such a result.
yeah. I mean, this is the result from this table. This result. So it produces a significant result. So then you can just interpret this result.
Do some researchers follow this strategy?
Yes, they are.
Oh, I see.
Just then you can find those research maybe, like and then you can just like look at them and then the analysis and then their interpretations. You can look at their datas and how things are changing. And remember that I showed to you the effect size study that we have. Even if the people are doing the right things, because they haven't presented the effect size, their results were totally different. Their interpretation would be different too. Their interpretation would totally be different than what it really is. But statistically, it's producing significant results. So that's important. I mean,
Very risky.
yes, choosing the right analysis, choosing the right research design, starting from that, is the most important thing. And if you don't do right things, your interpretation will be wrong.
Even if it sounds right.
I mean, if it sounds right. So this doesn't make it sound right. This is just number. The computer doesn't understand whether this variable is normal or not. So for that reason, we are going to be the one who are investigating and or making this right in order to interpret it right.
But doesn't SPSS warn the user?
No.
In Needworks, it won't.
What
It won't.
in SPSS you gave Burgundy as 1, Bordeaux 2, and Rhône as 3, and just like Languedoc as 4, for example.
How will it know that's
You can write as nominal variable. In SPSS, I haven't used that one. There are cases that SPSS suggests you the analysis type if you give the type of the variable, those kind of things. I haven't practiced it. I'm not sure how good is that. Probably it's working good. You can try that if you just like label the variables in here. That might help too. But other than that, if you say SPSS do that, SPSS will do it for you. Kurşun asker.